Good morning, everyone. After reviewing some concepts from the trigonometry unit in advanced functions last Thursday, now we are ready to start talking about how to take derivatives with sine and cosine and the other trig functions. Okay, and I said the reason we spent a little bit of time on this is because there's some additional rules we have to learn. Basically, there's some special cases. And once we know those cases and combine those with the rules we already know how to use, like product rule, chain rule, quotient rule, then we can take the derivative of any trig function. Okay. So this next little part is just a visual demonstration. You don't have to copy it down, but I want you to reason it through a little bit here. So we're going to talk about the derivative of sine, which I know some of you have already figured out either through the last assignment or in talking to me on the side a little bit. Okay, but here's the graph of sine, and as a thought experiment, let's try to think of what the derivative of this would look like. Okay, so the first thing we're going to talk about is where would the derivative of this be 0? Okay, and of course that's everywhere there's a max or a min. So for example, at pi over 2, right here, sine has a max, so that's where the tangent would be 0. So my derivative would be 0 at about pi over 2. And I apologize that I can't seem to point directly on that. We'll try that one more time. Okay. So similarly, here at 3 pi over 2, that would be local min. Okay. And so we'd have a 0 there. Okay. Everywhere I see a max, there's going to be a 0 in the derivative. Okay. That's good so far. Next thing we're going to think about is where is the tangent line the steepest? Okay. So for example, here around 0, right, the tangent lines, right, they're lower, a little steeper, a little steeper, a little steeper, and it kind of looks like around 0 is where they start to switch and go the other way, right? That's really where our inflection point would be, is right there. Okay, now we don't know exactly what its slope is, but for the sake of argument, let's say it was 1 right there. Okay, it does look almost like it's 45 degrees. So let's say that slope was 1. So that means I have a slope of 1, so my derivative should be 1. Okay, over here at pi, going the opposite direction, okay, this one looks like it's about -1. It's probably my biggest slope. So here I would have -1. At 2 pi, it's going up again. I'd have +1. Okay, back here at -pi, I would have -1. Okay, +1. So if I start connecting the dots, this looks kind of familiar. Okay, it would appear that the derivative of sine is cosine. Okay, and we end up with the same kind of wave pattern there. Okay, right? Derivative of trig function is a different trig function. Okay, so on another day we're going to go through the actual formal proof of why this works. Okay, but for right now, we're going to just kind of go with our instinct here. And that's what it actually is. So these are the two rules that you really need. Okay, and this is the first one. So make sure you just learn these off the top of your head. Okay, the derivative of sine is cosine. Okay, so whenever you see sine and you need to take its derivative, it's just going to be cosine. Okay, flipping it around. Okay, for cosine, okay, almost the same idea. There's a little tweak. The derivative of cosine is negative sine x. Okay, it's negative sine. Okay, and again, as a quick little visual as to why that would be, right, cosine starts at a max and starts going down. So when its derivative, it has a 0 at first, but then it has the maximum negative slope, so down. So it's sine, but it starts going down instead of up. So it's going to be negative sine. Okay, so those are the only two ones you just have to remember. Okay, the derivative of sine is cos, and the derivative of cosine is sine. All the other trig derivatives we can figure out with those two rules, one of which we'll do in a moment or two here. Okay, so the rest of this lesson is just going to be showing you some examples of some expressions that involve trig and taking their derivative. And then your homework is basically just going to be practicing the skill. Okay, practice, practice, practice. Get used to differentiating sine and cosine. So here we go. Okay, first one. Okay, instead of just plain sine x, we have 2 sine x. So f prime of x. Okay, well, only thing here we have, the only difference is we have a constant times that. So in hopefully from our work we can remember, when we have a constant multiple of some function, I can just leave the constant alone. So it's still 2, and now just do the derivative of sine. So the derivative of sine is cosine. So the derivative of 2 sine x is 2 cosine x. And that's basically it. Okay, and maybe a brief reminder to everyone running this, just pause the video whenever you need to make sure people copy things down. And then we'll just kind of move on to the next thing. So here is the next function. Sine x, cos x. Okay. Key thing with this one, right? I can really think I have 2 functions here, sine and cos side by side. They're being multiplied together. So that means I have to use, yes, that's right, the product rule. So f prime of x is equal to, okay, derivative of the first. The derivative of sine is cosine of x, and we leave the second alone, cos x. Plus, we leave the first alone, sine x. What's the derivative of cosine? It is negative sine x. Okay, now let's do some tidying. So cos of x twice there, that's cos squared of x. And now let's subtract sine times sine is sine squared x. Now take a moment, and maybe this will be a good place to pause for a second. Go to that list of identities you have. Does cos squared x minus sine squared x look familiar at all? Okay, and if you dig a little bit, okay, you will find that that is actually cos of 2x. Okay, so as I said on Thursday, one of the reasons we have all the identity stuff is so I can do this. I can take a messy looking expression like cos squared x minus sine squared x and make something much simpler. So if I want to do some analysis, it's much easier to use cos 2x than that other expression. Okay, let's go on to the next one. Okay, speaking of double angles, here's sine of 2x. Now, we don't have to use identities to expand this out, and I would almost never recommend doing that. I'll just start our work here. Okay, key thing to note though, because we have a different argument, okay, this is kind of our inner function. Okay, so this is going back to chain rule. If I let u equal 2x, what I really have here is sine of u. So if I want to do the derivative, I do sine of u, get that, and then do the derivative of the inside. Okay, I'm not going to write that out here, but that's the idea. Okay, my outer function is sine, and my inner function is 2x. So what's the derivative of sine of something? The derivative of sine of something is cosine of that something, so cos 2x. Okay, and the derivative of the inside, okay, which is 2x, is just 2. So my derivative is 2 cos 2x, and that's done. All right, another interesting one, cos squared x. Okay, to give this a little bit of context, and we usually don't write it this way, I'm just going to take a moment to rewrite that. Okay, f of x, cos squared x, and we almost never write it this way, really means cos x all squared, right? That's really what it means. It was cos x times cos x. So again, this means I have to do the chain rule when I'm doing my derivative, but the other way. Okay, my outer function is something squared, and my inner function is cosine. So derivative is something squared, well, that's 2 times that something, and drop the power by 1. And now for the derivative of the inside, the derivative of cos is negative sine of x. Okay, let's do some tidying. Okay, negative can come out front, so this is negative 2, and just to help see it, this is negative 2 sine x cos x. And once again, if we go to our identities, okay, 2 sine x cos x, that is the formula for sine 2x. Okay, and we're done. So derivative of cos squared x is negative sine 2x. Okay, last but not least, let's do tangent. Okay. Now, we don't have a rule for tangent. We only have for sine and cos, but that's not a problem because we know that tan is equal to sine x over cos x. So to do the derivative of tan, okay, we're just going to take that and use the quotient rule. So f of x is equal to derivative of the top. The derivative of the top is cos of x. X. Okay, minus the top, sine of x, times the derivative of the bottom, negative sine x. Okay, all over the bottom squared, so cos x or cos squared x. Okay, let's do some tidying. In the top, I have cos squared x. I have a negative and a negative sign inside, so that's plus. Sine times sine is sine squared x, and that's over cos squared x. Now, hopefully, I can hear you jumping up and down because there's another little identity in there. The numerator, cos squared plus sine squared, well, that's really just 1. So that's 1 over cos squared x. Okay, and cos squared, 1 over cosine is really secant. So secant squared x. And we're done. Okay, that is the derivative of tan, secant squared x. So a little experiment. You might want to try working out what the derivatives of cosecant and secant and cotangent are and see what those are. Okay, so that's the end of the lesson. Okay, it's just going through the rules. So here is a whole bunch of practice. Okay, on these 2 pages, page 225 and page 231, that will get you practicing the skill of taking derivatives of sine and cosine. So this is what I want you to work on for the rest of the period. And feel free to get into small groups and go up onto the whiteboards and work together and start working these things through. I would, I'd encourage you to do that if you would like to. Okay, so thanks for watching, and I hope to see you tomorrow.